Okay, so in this video, we'll talk about the EMF induced by changing magnetic flux density B. Okay, so a circular coil and a long straight wire carrying current are fixed near each other. This is the circular coil. This is the straight wire carrying current. And then you know that the magnetic flux density due to a straight current carrying wire is this. Okay, so by using the right hand grip rule, you know that the magnetic flux density due to this straight current carrying wire is into the page. Okay, and then the B is equal to mu naught I over 2 pi r, where the r is the distance from the wire. Okay, which statement is true about the induced current in the coil when the magnitude of the current in the wire is increasing? Okay, when the current is increasing, you know that B is also increasing. And then from Faraday's law, you know that Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux linkage. Okay, so when there is a change of magnetic flux linkage with the circular coil, then you know that there is an induced EMF in the circular coil. Okay, which statement is true about the induced current in the coil when the magnitude of the current in the wire is increasing? Okay, B is increasing. So you know that the induced magnetic field should be out of the page. Okay, which is the induced magnetic field. Okay, so the induced current should be in anti-clockwise direction. Okay, because from the right hand grip rule, you want your induced magnetic field to out of the page. Okay, to reduce the increasing magnetic flux. Okay, so this is the correct answer. A metal frame PQRS of area 4 times 10 power 2 cm square and resistance 4 ohm is placed in a uniform magnetic field of 2 Tesla. Okay, if the magnetic field decreases to 0 at a constant rate in 0.5 seconds, what is the magnitude and direction of the induced current? Okay, so you know that B is decreasing. So your induced magnetic field should be in the same current, in the same direction. Okay, so this is the direction of the induced magnetic field. Therefore, the direction of the induced current should be this way: P to Q to R to S to P again. Okay, because when you are using your right hand grip rule, you want your induced magnetic field to be into the page also. Okay, so by using this equation, remember that this equation represents both Faraday's law and also Lenz's law. Okay, so you know that you only have one term here, so n equal to 1. And then phi equal to B dot A. And then now you know that B is in the same direction as area vector, okay? Because B is into the page, and then the area vector is also into the page, so you can get rid of the dot product. Okay, so by using the partial derivative, you get this. And then you know that the area of the PQRS is not changing, so dA equal to 0. Okay, so dB over dt is like this. Okay, from 2 Tesla to nothing in 0.5 seconds. Okay, and then the area is 4 times 10 power 2 cm square. Okay, you change it into meter square. Okay, so you can get the magnitude of the induced EMF. And then you notice that we don't care about the negative sign here. Okay, because I just want to find out the magnitude of the induced EMF. And then induced EMF equal to induced current times the resistance. So you can get the value of the induced current. Okay, so you know that the induced current is in this way to reduce the decreasing magnetic flux. Okay, which means the direction of the induced magnetic field must be in the same direction as the external magnetic field. Okay, but actually I think I write this wrongly. I should write 0 minus 2, okay? I should write negative 0 minus 2 over 0.5. But you know, normally when we are trying to find the EMF, we really don't care about the sign of the EMF anymore. That means that I only want to know the magnitude of the EMF, and then the direction of the current I can easily find from the right-hand grid rule and also the Lenz's law. So I should write 0 minus 2, okay, because this is the final magnetic flux density minus the initial flux density. The graph below shows the variation of a magnetic field B with time. Okay, when time equal to 0, B equal to 0.2 Tesla. When time equal to 5 seconds, the magnetic flux density equal to 1.2 Tesla. If a circular loop of wire of radius 50 cm is placed in a magnetic field with its plane perpendicular to the field, what is the induced EMF in the loop? Okay, so by using this equation, okay, and then once again you know that dA equal to 0 because area is not changing, so A is a constant, so dA equal to 0. So dB is what? Is 1.2 minus 0.2 in 5 seconds, and then the area is pi r squared. So you can get the magnitude of the induced EMF, and then you notice that I ignore the negative sign, okay, because I only care about the magnitude of the induced EMF. A circular coil of 50 turns is placed horizontally. Okay, so this is the coil, and then you know that the magnetic field is in this direction. The radius of the coil is 8 cm. A magnetic field of flux density 0.05 Tesla passes perpendicularly through the coil. The magnetic flux density is then increased to 0.1 Tesla in 40 milliseconds. Find the induced EMF and then determine the direction of the induced current and explain your answer. Okay, so by using this equation, which represents both Faraday's law and also Lenz's law, and then you know that phi equal to B dot A, and then you know that the direction of B is exactly the same direction as the area vector, okay, because B is downward and then the area vector is also downward, so they are in the same direction, so you can get rid of the dot product. Okay, so you do your partial derivative, and then you notice that the number of turns does not change, so dN equal to 0. And then the area of the coil also does not change, so dA equal to 0. So these two terms is 0. Okay, so N equal to 50. dB over dt is 0.1 Tesla minus 0.05 Tesla. Okay, this is the final magnetic flux density. This is the initial magnetic flux density, okay, divided by time in 14 milliseconds, and then area is pi r squared. Okay, so you know the magnitude of the induced EMF is this. Okay, once again you can also ignore the negative sign if you want. So okay, you know that the external magnetic field is increasing, so your induced magnetic field should be in upward direction. Okay, so this is your induced magnetic field. Okay, so remember that induced magnetic field is the magnetic field caused by the induced current, and then by using the right hand grid rule, you know that the direction of the induced current should be this way. Okay, so that the induced magnetic field is upward. Okay, the induced current is in anti-clockwise direction to induce upwards magnetic field in order to oppose the increase of magnetic flux linkage. Okay, a thin circular coil of diameter 30 cm and 400 turns is located in a magnetic field such that the plane of the coil is perpendicular to the magnetic field of 40 millitesla. Okay, so it's like this. The plane is here, and then the magnetic field is in this direction. So you know that the plane is perpendicular to the magnetic field. The magnetic field is then reduced to 0 in 2 seconds. Okay, so let's say the magnetic field is directed into the page. You know that the magnetic field is decreasing. So you want your induced magnetic field to be into the page also. Okay, this is the direction of the induced magnetic field. Okay, and then by using the right hand grip rule, you want your induced current to be in clockwise direction. Okay, so that the induced magnetic field is into the page. Okay, so please find the induced EMF in the coil. Okay, by using this equation, and then you know that phi equal to B dot A, and then you know that since B is parallel to A, then you can get rid of the dot product. And then by using partial derivative, you get this. Okay, so you can get the magnitude of the induced EMF. Please find the magnitude and direction of the induced current in the coil if the total resistance of the coil is 0.5 ohm and the magnetic field is directed into the page. Okay, so E equal to IR. E is the induced EMF and then I is the induced current. So you can find the magnitude of the induced current. Okay, and then just now I explained how you get the direction of the induced current. A solenoid of negligible resistance is connected to a resistor of 4 ohm. Okay, a bar magnet is placed inside the solenoid. Explain why the current is induced in the circuit when the bar magnet is pulled out in the direction of B. Okay, when the bar magnet is pulled out in the direction of B, the magnetic flux of the solenoid changes. So this produces an induced EMF and hence produces an induced current. Okay, because you know that the Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux linkage. So when there's a change in the magnetic flux linkage, there must be some induced EMF. Okay, and then when the circuit is completed, then the current can flow, and then the current is called induced current. By using Lenz's law, explain how the direction of the induced current in the resistor can be determined. Okay, you recall that Lenz's law states that the induced current will flow in a direction such that the magnetic field produced by the induced current will always oppose the changing magnetic flux that produces the induced current. Okay, so the induced current in the solenoid will flow in such a way as to oppose the motion of the magnet. As the north pole of the magnet is leaving the solenoid, the induced current will form a south pole on the right end of the solenoid. Okay, that means that this is the north pole of bar magnet, and then so here must be south pole of the solenoid, so that the solenoid can attract the bar magnet when the bar magnet is leaving the solenoid. And then you recall that what we have learned in the last video. When you want to push the bar magnet towards the solenoid, then the solenoid does not want you to approach the solenoid, so that the solenoid will try to repel you. And then when you try to leave the solenoid, then the solenoid wants to attract you, so that you cannot leave from the solenoid. Okay, so now this is this case when you are leaving the solenoid, but the solenoid does not want you to leave the solenoid. Okay, so when you know that this is south pole and this is north pole, then the direction of the current should be this way. Okay, because when you are looking at the solenoid from this direction, when this is south pole, then the current will be in clockwise direction. And then when you look at the solenoid from here, when this is north pole of the solenoid, then you can notice that the current will flow in anti-clockwise direction. Okay. So the induced current will flow through the resistor from right to left. If the initial magnetic flux linkage which passes through the solenoid is 4 Weber and the bar magnet is pulled out completely from the solenoid in 2 seconds, find the average induced current which flows through the resistor. Okay, so you find the magnitude of the induced EMF first, then only you try to find the magnitude of the induced current.